I really like the comments that I've seen on the last video we did where we showed the relationship between the sequence of squares and sequence of odd numbers and symbols, so I want to follow up a little bit based on your comments. So just to review, sequence of odd numbers, sequence of squares. Here is how you build the sequence of squares from the sequence of odd numbers by addition. If I add the first 3 odd numbers, third square. If I add the first 4 odd numbers, fourth square. If I was to add the first 5 odd numbers, I'd get the fifth square. Okay, we looked at this. Here it is numerically. We looked at it in words from Fibonacci's Book of Squares in the year 1250. We looked at it again from a piece of art that I saw at the Walker Art Center in Minneapolis. And then we did it this way in symbols. So it's 1 plus 3 plus 5 up to 2n minus 1, which is the nth term. This says if you add the first n terms in the sequence of odd numbers, you get n squared, which is the nth term in the sequence of squares. So this line right here is the relationship in symbols. Now some people wrote in and said, gee, I thought you were going to just go right to summation notation or sigma notation from there, and you know what? I was going to do exactly that, but I kind of ran out of room and I thought the video is good enough as it is, so I didn't go any further. But if we did, there's a nice notation for this that says, where we use the summation notation, it says the sum of all of these things from k equal 1 to k equal n is equal to n squared. And what are these things? Well, when k is 1, 2 times 1 is 2, minus 1 is 1. When k is equal to 2, 2 times 2 is 4, minus 1 is 3. When k is 3, 2 times 3 is 6, minus 1 is 5. So this is a way to write the sum of the first n terms in the sequence of squares. Okay, so that comes out to be n squared. Here's another way to write the relationship here in symbols using summation notation. Now somebody else wrote in and said, I thought you were going to prove it using mathematical induction. I think that's a great observation. What we've done right here is using inductive reasoning. So we're saying it looks like there's a pattern here, and I can use inductive reasoning to say, look, I could go to add the first 5 terms, first 6 terms, first 7 terms. I'm going to get 5 squared, 6 squared, 7 squared. But is it true for all the rest of the infinite number of terms in the sequence of squares and the sequence of odd numbers? To show that this is always true, we have to use a kind of deductive proof. One of those is called proof by induction. So I'm just going to run through that real quickly. Not something that you see usually until you're in pre-calculus, something like that, but great method of proving things. It goes like this. You have to show whatever it is you're trying to show works when k is equal to 1. Well, when k is equal to 1, or n is equal to 1, that just gives you the first odd number and the first square. So 1 is equal to 1. Yes, it works when n is equal to 1. Then you assume that it works for some integer k, for n equal to k, meaning that this is true. There's some value of k that this works for. Then, assuming this, you have to show that it works when n is equal to k plus 1. If it works for n equal k, it works for the next consecutive integer after that k plus 1. So, does it work here when n is 1? Yes. Assume that it works for n equal k. I'm just going to make that assumption. Now I have to show that this is true. So here's what the relationship looks like if I go one more term. I go up to 2k minus 1, the next term after that is 2k plus 1. If this is k, if I put in k plus 1 here, 2 times that minus 1 is 2k plus 1. And what's the next term on this side? It's going to be k plus 1 squared. So can I show that this is true? Watch, it's really easy. So look, what is this right here? That happens to be n squared. That was my assumption right there. Whoop, take that back. That's equal to k squared. That was my assumption. I assumed that this was equal to k squared plus 2k plus 1. Well, what's k squared plus 2k plus 1? It's k plus 1 quantity squared. So I have in fact shown that if this is true, then this side over here has to be true, because this plus this is equal to k plus 1 squared, and that's what I'm trying to show is true. So by mathematical induction, very easy to show it. So I like the comments. It's exactly the progression of things that I would have done if I had been thinking a little bit more about it. I was going to use summation notation. I didn't even think to do mathematical induction, because generally this is kind of a hard thing for people to understand if they don't have much experience with it. But since you asked, here it is, proof by mathematical induction. So, a little bit more about the relationship between the sequence of squares and the sequence of odd numbers.